And last class period, we set everything up, right? In fact, we even calculated the initial concentration of whatever conjugate acid or conjugate base is going to control the pH. So what we're going to do today is just write the Ka or Kb reaction, whatever that compound is. If it's a conjugate acid, we'll write a Ka reaction. If it's a conjugate base, we'll write a Kb reaction. And then to predict the pH, we're just going to do what for that Ka or Kb reaction? Do ice. That's all we're going to do. So we've already done the hard part, I think. Hard part is setting the stuff up. So I'd just like to review that a little bit. And since the calculations are kind of long, we're just going to, I think we should stay at our desks and not go to the boards. But so I think this is probably one of the most confusing parts. So you're titrating HCN with NaOH, okay? And the question is, what's the Ka or Kb chemical reaction that controls the pH? Right? It describes the equilibrium at the equivalence point for each titration. Ramiro, would it be a Ka or a Kb reaction for A? It would be he says a Kb reaction, right? A couple ways to figure it out, I think. One is you're adding NaOH, that reacts with this acidic hydrogen, and you're left with a conjugate base. Another way to think of it is add a base, get a base, right? So either way works. You have to write a Kb reaction. So he's right. AJ, what Kb reaction is going to be controlling the pH? Now, HCN is gone, though. No. Identify. So here's your weak acid. All right? And recognize him as the conjugate acid or conjugate base, as the conjugate acid. So he's a conjugate acid. He reacts with the NaOH. So we really don't even care about this thing. We just know that, oh, it's reacting with a base. So we're going to get the conjugate base. That's why I write the Kb reaction. So it's not HCN, but Cn minus. And then this part you got to just memorize. Because if you don't write the Kb reaction exactly how they want you to write it, that Kb number, whatever it is, whatever you calculate it to be or find it to be, it's going to be wrong. So you have to write the reaction this way. Otherwise, it's not a Kb reaction. The conjugate base plus water gives hydroxide and the conjugate acid. How about if we titrated, Eric, hydrofluoric acid with sodium hydroxide? Would you end up writing a Ka or a Kb reaction? Another Kb reaction. He's right. Lauren, what Kb reaction would you end up writing? F minus and H2O goes to what? OH negative and yeah, the conjugate acid. Yeah, I got lost. Conjugate acid. Okay. But Albert, life isn't always so straightforward. We're titrating, bless you, methylamine with HCl. Would you end up writing a Ka or a Kb reaction? He says Ka. Does everybody agree? Yeah, add an acid, get an acid. You're going to write a Ka reaction. Okay? I think the confusing part out of this is this bloody thing, right? I'm not asking you to memorize these things. Where would you find the chemical formula for this? The weak base table. And how do you know to look in the base table? Because it's reacting with an acid, exactly. So you know exactly what table to look. Save yourself some time. Oh, I got to look in that dang weak base table. Okay, so hopefully Vanessa has her notes. We need the Kb table, and then we got to find methylamine and see what its formula is. Yeah. Did you find it?
Yeah.
Oh, she already did. Okay, what is it? Two. Yeah, and they give us a Kb for it, right? So No, they'll write it down. What's the KB for it? Oh, no, the KB number. If you don't have it, don't worry about it. But it's a number that's in the table, right? Does everyone remember that kind of stuff? Okay. So now Albert said we were going to write a what reaction? A Ka. All right. So how do you write Ka reaction? What would you write? Victoria, what would you write? But CH3NH2 is the conjugate base. So you're close, just add an H. So where do you want to put the H? I like to put it in the front too. Because if you put it in the front, you can just erase it. Oh, there's the conjugate base. Put it back, conjugate acid. I like putting it right in the front also. HCH. You can really put the H anywhere, wherever you want. And it technically should be a plus too, because you started out with something neutral, and you add an H plus, you end up with a plus charge. And that's going to, for a Ka reaction, Jasmine, that goes to what and what?
H plus.
H plus and
CH3NH.
yeah. See, it's so much easier if you put that H out front, because you just rip it off to get the conjugate base. Okay. For the Ka reaction, there is no H2O. It's always the weak acid going to H plus the conjugate base. Yeah. No. It's the convention. It's the convention. There really is no rhyme or reason. It's just that we know that we need to calculate a Ka for this. And you get the tables to get it. And in fact, in this case, you're going to have to calculate it, right? Ka is going to be Kw over Kb, because we can't look up the Ka, right? So you're going to have a number for that Ka. But for that number to work in ice and to do your calculations, the reaction has to be written this way. Everybody has to write it, the acid going to H plus the conjugate base. If you want to change it, that's fine, but then that Ka number is going to change, and everyone has to follow the new convention. But this is just how they do it, so you just got to remember. Conjugate acid going to H plus A minus. It's kind of like this. But, I mean, in fact, I don't know if you'd realize this. You may not be comfortable doing it, but you can always just do that for ice. It doesn't matter how ugly it is. For this one, you could have just wrote A minus plus water gives hydroxide and HA and do ice. Who even cares what methylamine is? Because the ice doesn't care, right? Anyway. "12 grams of acetic acid." Okay. HC2H3O2 is acetic acid. Ka is 1.7 to 10 negative 5. I just got all that from the table. It was dissolved in 50 mils of water and titrated with 2.8 molar NaOH. So, Mari, at the equivalence point, you had just enough NaOH for all that acetic acid to react, every single little molecule of it. At the equivalence point, does acetic acid or the acetate anion dominate? Yeah, exactly, because all that acetic acid is gone. And what is its concentration? So Ramiro, we want to know what its concentration is. So where would you start on that? Yeah. Now guide yourself. Get a few little brownie points here. What did I like you to write? Do you remember this?
The actual thing, the 40.
In brackets, I would put C2H3O2 minus. And then do you remember what I wrote?
Moles over liters.
Close. Moles over liters is right. But there's nothing wrong with doing what Jasmine said. But if you write what Mari said, total liters, and get into the mode of doing this, it's going to remind you just what the heck you got to do. right? It really does. Okay. So, I don't know. AJ, you want to find the moles or the total liters first? So he wants to find the moles. So Eric, how are you going to get the moles? Mole bridge. What do you mean? That's it. Do you hear them? They gave you grams. You convert it into moles. That's not how we usually do these questions, right? Let me jump down. Here's a typical one, right? Here's a typical question. How do you get the moles? We just set up a big M equation, right? Remember doing this? Big M equals moles over liters, and then you just solve for your moles. You'd have 0.28 equals moles over 0.035. Remember doing that? But not in this case. He caught it. I didn't think he's going to catch that. Yeah, just molar mass. Convert the grams into moles, and you're done. Now, that's the moles of acetic acid. Why is that the moles of acetate also? Yeah, that's what we did. But we're interested in the concentration of the acetate. Where does the acetate come from? All the conjugate base comes from the conjugate acid. It's all converted. So the moles has to be the same. Right? Now the concentration's not the same because the volume changed. But the moles are the same. So okay, let's get the moles. We'll have 12 grams times, here's a question. Lauren, molar mass, Eric was right, add up all the molar masses of all the atomic molar masses, right? Okay, but here's my question to you. Do we add up the molar mass of this? Or do we add up the molar mass of this? Which one? Because they're differ by an H, right? Which one are we supposed to add up? It's the acid, because they said 12 grams of the acid, right? So we got to convert them into moles, and we're going to find the molar mass of this one. Okay. So an H, 2 carbons, 3 more hydrogens, and 2 oxygens, you get what? 32, 35. I don't know. I can't do anything in my head. Is it 60?
60.06 is
Okay. You guys believe Eric? 60 grams. 12 divided by 60 is like a fifth. That should be 0.2, right? Okay. So now we've got our top part. 0.2. Now we have to get our total liters. Okay, Albert, what are you going to do to get those total liters? Yeah? Oh. Yeah? Now, do you guys realize what he's doing? He's saving time. You can't, usually we end up starting, I'm going the wrong way. Usually you end up starting with the volume, and then we convert all the way to the other volume. But here, man, he caught it right off the bat. You can't do that here. You can't start with the 50 mils because you don't know what the concentration of that acid is. You can't do it. So he's exactly right. You start with the moles you calculated, and then I cut him off a little too early. I didn't let him finish. But you start with those moles. Then you said mole bridge. And then that's where I cut him off. But let's go ahead and start where he's at here. He said you're going to have 0.2 moles. Now, why are we doing this? Because this is really what plus what? The equivalence point is what he's after. The equivalence point plus now, Eric said the initial. How much is the initial? Yeah, 0.05. So we're after getting that equivalence point. Do you recognize the 0.05? That's 50 mils converted to liters. Here's our initial that Eric's talking about. Okay, so we have 0.2 moles of this acetate stuff, or acetic acid. It really doesn't matter which one you write. C2H3O2. It really doesn't matter which one you write, because all these reactions, all these mole bridges are what ratios? They're all 1 to 1. So it really doesn't matter what you want to write. They're always 1 to 1. To 1 mole of what? NaOH, yeah, whatever we're reacting it with, whatever's our titrant. NaOH or HCl, in this case it's NaOH. It's always they're always 1 to 1. Okay. Vanessa, this is where I cut Albert off. I would have let him finish. Hopefully, would he have said? What would he have done?
You could put the liters on top.
Yeah.
Over the 0.28 mole.
Yeah. Now let's say you're totally confused. You had no idea what to do. You knew you're after liters or volume, right? What's something you can always do to give you a hint? Now she's right, but I'm just saying you're totally lost, totally confused. You're so nervous on this test.
You equal it to liters.
Whatever's up on top has to be on the bottom. Also equal to liters, you're right. Equal to liters, you're right. That's going to be a big hint. But also what I was thinking of was what Alyssa was saying, is see how these guys are gone. Those units have to go on the bottom. Or doing what Jasmine says, that also works. Giving you a hint where you got to end up. But, right? Okay, so what do we get for that? 0.2 divided by 2.8, about 0.0714. So that equivalence point, 0.0714. So we can get our concentration of our acetate. It's going to be the 0.2 divided by plus 0.05, about 0.121. I end up about 1.65 or so. That's what they wanted. What is this initial concentration? Okay. Now you can make your life complicated, and I tried to do that by giving you all this, but I say, we've done this so much, right? You know what's there, and you know what's initial concentration. It's ice. And it's ice of a Ka or a Kb reaction. It's ice of a Kb reaction. So somehow you got to figure out what Kb is. You have to write the Kb reaction and do ice, and we figured out there's our initial concentration of our conjugate base. All right? So Kb reaction, C2H3O2 with a negative. You have to add it to water. You get the conjugate acid and hydroxide, right? And then do ice. And fill in that ice table. The 1.65 goes under the, yeah, the conjugate base. Fill it in. They're after pH. So hopefully our Kb number will be 10 to the negative 4 or smaller, and life will be good. See if you can fill out that ice table. Make things work. We'll stay away. Okay. Somebody needs a calculator? And you're going to have to tell me all your numbers. Oh, I can steal them. What was it? .88 times 10 to the negative 10. Shouldn't that be times 10 to the negative 10? So a couple folks got 5.88 times 10 to the negative 10 for their KB. What'd you get for your X? .11 times 10 negative 5. Okay. 3.11. Okay, make sure you can get that far. And then I want to show you something that's confusing. Happens a lot. I see this mistake a lot. Okay. Did everybody get it? 3.11 times 10 negative 5? Okay. Now, they're always after pH. You can take the negative, this work, tell me if you can answer this question, you see what I'm talking about. If you take the negative log of x, you get pH every single time for what type of reaction? A Ka reaction, right? So just remember that. If you take a, well, you don't really, I don't think you even have to remember it, because I end up looking at this ice table every time and seeing what x is. X in this case is OH. So you got to be careful. X is OH. So if you take the negative log of 3.11 times 10 to the negative 5, you just got POH, which is 4.51. So that means my pH is 13.5 or something. You got to subtract it from 4.5. See how I can't do any math in my head. Isn't that sad? PhD in chemistry. What is it? 9 point what? 9.49. Okay. pH plus pOH is 14. Make sense? Okay, so you try it. Now, you can follow these little steps, but I say you've done this so much, you really don't need those little steps. What is the pH at the equivalence point when 35 mils of 0.28 molar methylamine is titrated with 0.21 molar HCl? And I think it's very healthy in these questions to have a mode, and you approach it the exact same way every time. And how we've been doing that is we look at it and see if the solution is going to be acidic, basic, or neutral. Identify what that conjugate acid or conjugate base is that you're forming. And that's what you calculate the concentration of. It'll either be a conjugate acid or a conjugate base every single time. Yeah, no, he is CH3NH2, but you're adding HCl to him. So he's a base because he's in that base table. So that means he's gonna turn into his conjugate acid because that base is gonna react with that acid and make the conjugate acid. So this is gonna be an H, add an H to it. So that means you have to write a Ka reaction too. So if you're doing my little mode here, hopefully this is where you started out then. Was it H? All right, that's my starting point. Because it helps you identify everything you got to do. You recognize that the conjugate acids, you have to write a Ka reaction and do ice. You recognize how to get that initial concentration, moles over total liters, to put in the ice table. It looks all right. Check with Romero. See if you got it. 9.8 times 10 negative 3. Okay. So for the moles, I see a lot of people having 9.8 times 10 to the negative 3. And they just use this to get it. Right? And then to get that total liters, what would that be? 0.035 plus the equivalence point. Now, I don't know if you've noticed this, but you can save a little bit of time. To find the equivalence point, you really don't have to start here. You can save a little time by starting where? With those moles. You went through all the work to find them. You could just as well start with that 9.8 times 10 to the negative 3 moles and jump right to the mole bridge, but it really doesn't matter. I think it's good to approach it the same way every time, but be open to different ways too. It kind of helps. In fact, it is a lot quicker to start with those moles. So I'm going to do it that way. You get 0.046 liters for your, yeah, 0.047 or so. you get for your initial concentration? 0.012? Okay. I don't think it's right. What did you get for your initial concentration, Eric? 0.035? Did you get 0.035? 0.12? 0.12, 0.12, 0.12. You got it right, 0.12. Now you got... 0.12 big M. So you should be dividing the 9.8 times 10 negative 3 divided... Did you find it? Oh, okay, all right, but as long as you found it. All right, so then we have to do ice. Okay. Now we need a Ka. Can we look up Ka? No, can't look up Ka. Gotta calculate it. What is its Kb, Alyssa? What did you get for its Kb? 4.4 times 10 negative 4. Then what did you get for its Ka? 2.27 times 10 negative 4. Is that okay with folks? Alrighty. So that has to equal x squared all over 0.12 minus x. Do some math. And we should get x equal to... Vanessa, what did you get for your x? What you doing right now? Uh, 1.7 times 10 negative 6. Okay. Okay. Now I want pH, so can I just take the negative log of it? Yeah, because H plus is X. And then you get pH of what? 5.8? Okay. There's 5 minutes left on the exam. You went through this big, long question. Look at all this. You could just turn it in, or you could look at your answer. Does the 5.8 make sense? Is it worth going back and, oh, man, did you definitely... Because you could look at this, and you could say that I definitely screwed up. You could say you definitely screwed up if that pH is what? Bigger than 7. It has to be acidic. It's an acid. So it has to be less than 7. Right. So I would definitely go back if you got something bigger than 7. But that's the idea. Okay. So there's more here you can practice on. But, you know, that's the idea. So the idea, I think, is to identify what's reacting, write its conjugate, and that's what you determine the concentration of. Moles over total liters. Write ice and get the pH. So enjoy your break.